it has to be 10 newtons. I can get rid of A and B. And now the question is it to the left or to the right? And since I have the bigger vector over here, it's going to be 10 newtons to the right, D. All right, let's try this one. All right, feel free to ask your neighbor if you're uncertain. All right, let's stop at 40 seconds. 40. All right, good. D is right. That's your insertion point. So in fact, if I gave you a figure with, say, the arm, right? You have a point where the muscles are attached here. That would be what? The insertion point, because that's the bone that moves. Up here, this is your origin, sort of where your bicep is attached to your upper arm. And then the axis of rotation will be at your elbow. There really is no torque point. That's not a thing. Let's do the one with the guy all bent over. This was actually a picture of me, and I used it for this quiz. You know, tell it looks just like me. The force due to the muscles, that's this force right here. What kind of torque do they cause? This figure's from your book. It's not actually. It's just a fine book. All right, let's stop at 43. 43. Good job. A is right. Oops. It's a counterclockwise torque. This force right here causes a torque in this direction. You can always put a pencil here and sort of pull up on it. And this torque primarily, or this force, Fm, primarily causes a small torque. Why? Why does it primarily, why does it cause a small torque? What about that force makes the torque really small? The angle, right? Is that a shallow angle? Remember with the door, you can get a small torque by applying close to the hinge or by applying far away from the hinge but at an angle. So that is a clockwise torque. Isn't that what y'all put? Yeah. Okay. Let's do the erector spinae muscles. What does that help us do? All right, let's stop at 28. 28. Oh, look at you. Awesome. Why do gingerbread men never wear shorts? Have you ever seen a gingerbread man in shorts? They have crummy legs. All right. I know that you might be inclined to lift heavy objects, but that's in fact what you're not supposed to do with your erector spinae muscle. You're not supposed to do like this guy, where you bend over and then you lift it like that, right? How are you supposed to lift heavy objects? You're supposed to use your legs, right? Not your erector spinae muscles, because they need to be strong, but they're not terribly strong, not like your legs are. Okay? So don't do like I did in this picture. Instead, pick up heavy objects like that. Okay? That's what? Like this guy, like I do? Good. All right, friction is a force that what? doing this one about friction. All right, we'll stop at 28. C is right. Friction will always oppose the motion. So if I, for example, pull this desk, I'm applying a force in this direction, and the frictional force, which is slowing down the motion, is in the opposite direction. The frictional force is always opposite the motion. Let's do the center of mass one here on the left. This is a wedge of wood. Which arrow points closest to the center of gravity? Oh, you know how to. Where's most of the mass? Or where can you imagine the center of the mass to be? All right, let's stop at 40. That's everybody. Okay, C is right. Listen, there is a mathematical definition for center of mass, and it's kind of complicated. It has to do with the product of a little piece of mass. Like you would break this into little bitty pieces of mass, and then you would ask, what is the product of that mass times the distance? And then there's this optimization where you find the center of mass. But we can look at objects like this and sort of think about where the center of mass is. Let's just do a few examples, since some of you seem to be uncertain if it was C or D. So if I have a symmetrical object like this, it's always going to be at the actual center. So if I have a square, or if I have a block, it's always going to be right in the middle. But if I have something that's not symmetrical, like this object, this wedge right here, the center of mass is going to be nearer to the point where you have the most mass, but not all the way at the end. Because if I go down here, I have a big long distance from this part. I want to sort of pick the point that's sort of in between. Where's my meter stick? Look, I'm going to take this meter stick. Normally, if I find the center of mass, it's right there, right at 50 centimeters. By the way, do you know that you could do that? The way that the frictional forces and the normal forces work, that if you take an object, like this, for example, and I move my fingers, they will always meet the center of mass. Do you know that? Yeah, it's kind of cool. It has to do with, I said, as I move my fingers, the frictional force between my finger and the meter stick changes because the normal force. It's because of the way that the forces are distributed on the meter stick onto my fingers, and they'll move until they get right to the center of mass. But if I add a mass, I'll add my key to it. Oh, it's not going to work. If I add a mass like that, now the center of mass is no longer going to be at 50 centimeters. Where is it going to be? Is it going to be at the location of the key? Where do you think it's going to be? Did it be to this side of the key or this side of the key? This side. Let's try it. Yeah, it's at about 45 or 6 centimeters. So it's not at the position where all the mass is, but it's sort of shifted or skewed away from where the original center of mass was. Listen, look back at the old test. I had lots of different questions about it, where I give you different figures and ask you the center of mass, and then also in the notes too, we had several. And then also remember about the body, how we said that this is our center of mass when we're just standing like this, but if we do something like this, then our center of mass moves out from over our feet. That's why we have to shift like this, and why we can't go up against the wall like we did last time. If I bend over, my center of mass actually comes out in front of my waist, outside of my body. That's why when you bend over, usually stick your bum out. Never use that word. I heard that recently. That's why it's kind of hard to bend over when you're actually up against the wall, because you're not allowed to move your backside out. All right. Yeah. Feel okay with center of mass? Feel okay with it? All right. Let's do this problem with the seesaw. You will see an equilibrium problem like this, a rotational equilibrium for a class 1, 2, or 3 lever. This is a class what? Seesaw, what is it? This one. All right, doing really well. I'm going to stop at 40. Just a couple more seconds. Guess if you're not sure. All right. Awesome. C is right. Whenever you encounter these, I'll probably give you a figure, but if not, just draw a figure. I got the big kid over here. Oh no, that was the little kid. So that's the little kid is 2 meters. And then I want to ask myself, where do I need to put the big kid in order to balance this out? And we've all used the seesaw. We know that the big kid needs to be closer. So the big kid is over here. I don't know what this answer is, X, but I know that it's smaller than 2 meters. So I know that it's not, or no, it could be that. I know that it's not A. It's either B, C, or D. And now I can sort of figure it out. I can calculate it. The torque on this side has to equal the torque on this side. That's going to be 50 times 2 is equal to 100 times X. 50 times 2 is 100. 100 is equal to 100 times 1. All right, so the answer is B for that one. So a pony walks into a bar, and he says to the bartender, "Hey, give me a drink." And the bartender says, "What?" And the pony says, "Hey, give me a drink." And the bartender says, "What?" And the pony says, "Sorry, I'm just a little horse." All right, y'all are going to be fine on this part of the test. I'm not worried. The reading quizzes help prepare you for it. Make sure you study over the old test. Make sure you read through your notes. In fact, hey, every night before you go to bed, I like to read. Don't you read before bed? Read your book before bed. That's a great idea. What's that? Oh, C. Yeah. Read your book before you go to bed. Just spend a little bit of time every day. Not a hard class. If you just take that tip. 20 minutes every day, just a little bit, sort of review some of the old tests, review your quizzes, review the notes, read through the book a few times, take little notes on the book on big ideas. Read the book before you come to class. That's awesome. All right? Okay. Let's move on to fluids and pressure. A lot of cool stuff in this chapter because, well, we have a lot of fluids in our body, and so there's good application of them. Pressure, many of you know, you saw it on the quiz, is a force per unit area. Pressure is required to move a fluid. Anytime we want to move a fluid, we have to have some difference in pressure, because fluid will always move from high to low pressure. Fluid here means anything that is either a liquid or a gas. So a fluid is something that flows. That's where the word comes from. It's a fluid is either a liquid or a gas. So for example, whenever we want to move a fluid, that includes things like breathing, because air is a fluid. We'll talk about breathing and how breathing operates by Boyle's law, or rather Boyle's law helps us to describe the action of breathing. Blood flow. We'll see how blood is a little bit different from other fluids because it's a viscous fluid. It's thick, like maple syrup. And so we will use the Poisy. You like how I said that? Poisy. Do I sound French when I say that? The Poisy law to describe how viscous fluids flow. And we'll apply that to blood flow. Digestion. We'll talk about the different kinds of muscles and how they move fluids. What kind of muscles are used in the digestive system? Smooth, right? Remember we had 3 different kinds of muscles from chapter 1? Cardiac, smooth, and what was the third? Skeletal, right? Make sure you know those. The sort of identification things for the test. Digestion, and then delivering medication. We'll sort of touch on that. We won't go quite into the same depth as the book. All right, the definition for pressure. Look, whenever I write a P, most of the time I'll put a little base on it, because later we're going to see the Greek letter rho, and my rho and my P look a lot alike. So I'll put a little table or a little base on my P. So P is equal to F over A, and the units of pressure are the Pascal. 1 Pascal is abbreviated PA. Whenever you have a unit in science, if it's a person's name, when you abbreviate it, it takes a capital letter. Like a Newton is capital N. Pascal is named after the mathematician and philosopher, and so it's a capital PA. And then that's also equivalent to 1 Newton per square meter. We'll also see some other units for pressure, and you're probably familiar with at least some of these. Inches or millimeters of mercury. You ever seen, I don't think hospitals use these anymore, but they used to. They might still use them some places, where you take your blood pressure, you see the little tube of mercury that goes up, that's measuring pressure, and it's relating the height of that column of mercury in millimeters to the actual pressure of the blood in your body. And we'll figure out where that comes from. Like, how is pressure related to the height of a column of fluid? It's actually fairly simple. So millimeters of hydrogen, and then based on that same thing, we have some others. I'm going to put these in parentheses. You can do inches. Did I say hydrogen? Mercury. Inches of mercury. Centimeters of H2O. Yeah, those are sort of the big ones. And those are similar, where instead of measuring the height of the column of mercury in millimeters, you measure it in inches. And instead of using mercury, you use water instead. Though there are inherent problems with measuring pressure with a column of water. And we'll watch a video about that, a Erector video. Y'all watch any more on your own? He's really good. He makes some really good stuff there. Did I tell y'all how I met him? I did. Like this. Me and Derek Miller. So we'll see a video about how that's problematic to use water or a fluid that's not as dense as mercury to measure pressures because of the immense atmospheric pressure. That's another unit that we'll use, is the atmosphere. 1 atmosphere, that's the pressure that we feel right now. And 1 atmosphere, well, what would you guess? Like, you know, a Pascal is a Newton per square meter. So this floor right here, this tile, is about a square meter. That means that if there's 1 Pascal of pressure, that means there's a total net force of 1 Newton of being applied to this 1 meter area. You follow what I'm saying? It'd be like having a quarter pounder, because a Newton is about a quarter pound, right? You'll know that? So next time you go to McDonald's, you don't ask for a quarter pounder, you ask for a Newton or a Newton burger, because it's about the same. But if you put a quarter pounder or 1 Newton on here, then you would get about a Pascal of pressure. So what do you think then is the atmospheric pressure? Like, what is the atmosphere, at 1 atmosphere right here in the atmosphere that we feel, what would you guess is the atmospheric pressure in pascals? Just go out. 10, 20, 10, 5, less? That means that if there were 10 pascals of pressure, that means that the atmosphere would be exerting 10 newtons of force on this 1 square meter block on the floor. 10.5? That seems reasonable. You ready to hear the real answer? Are you ready? Are you ready?
I'm ready.
It's 100,000 pascals. So the atmosphere is exerting on this little block of floor, which is 1 square meter, it is exerting 100,000 newtons of force. It's like 500,000 quarter-pounders on this little square. Football players about 1,000 newtons, so it's like 100 football players standing on this square. We'll talk about that, like where that pressure comes from. So the atmosphere is equivalent to 100,000 pascals, or newtons per square meter. All right, before we move on, I want to just remind you of how we calculate area. At a very base level, area is equal to some length times some width. Right, so a square is the side square, a rectangle is the length of the rectangle times the height of the rectangle. And area is a length times a width. Similarly, if I'm doing a volume, that's length times width times height. Y'all know this, right? You know this? You know this? So for example, if I have a rectangular prism, like that, it's going to be this length times this width times this height. Likewise, if I have a circle, the area of a circle is pi r squared. And I can think of this dimensionally, because I know area is length times width, that's a distance times a distance, and so this is a distance times a distance. And then if I want to know the volume of a cylinder, the volume of the cylinder is equal to the area of the circle times the height. So it's whatever this area is times that height. It turns out to be pi r squared times h. Because the area of that circle is pi r squared, and then I just multiply it through by the height for the column. If you have to calculate an area, you'll have to do so for, a simple shape. I won't have to make you do the square or the pi or any of that business. Although a length times a width is a squared number, right? Did you know that ancient peoples, not that long ago, 500, 400 years ago, that they thought squared numbers were evil, like literally evil, that they thought that there was some dark forces at battle over squared numbers. And you might think the same too, right? Y'all think they're bad, squared numbers? It was kind of silly for these people to think that they were bad. Why was it silly for ancient peoples to think that squared numbers were evil? How did they use squared numbers every single day? That is, what did they do? What do they spend most of their time doing? And we have to do hardly none at all. Getting what? Food, right? They have to get food. And so they were mainly agrarian, they mainly farmed, and when you're farming, you have to measure the area of your fields and calculate the yield so that you'll know if you make enough money. We'll see that a little bit later, I think in the next chapter, actually. Okay, so there are three possible sources of pressure in a fluid. The weight of the fluid, which we'll look at first. The external force applied to the fluid. we'll see this is related to Pascal's principle. And it is the principle that describes how hydraulic lifts work, which a lot of us use in a variety of things. We use them in our car, right, for our braking systems. We use them to lift people. Use hydraulic lifts for a number of different things. And then also the internal force due to the interaction of molecules. I think that was on your quiz today. So when we have a substance, like say for example, if we, I don't know, heat it up, if we heat it up, it makes those molecules move faster, and then that will increase the pressure. And we'll see that as it's played out in the ideal gas law. That's PV equals nRT. You've probably seen the ideal gas law. We'll look at it. Mainly we'll look at the relationships between P and V. That's Boyle's law. And then P and V with T. Which is Charles' law? I forget. Do y'all remember? I know it's Charles' law, but what is it? Is it PV and T? Or is it like P and T? I think it's P and T. It doesn't really matter. But we'll look at Boyle's law and we'll look at Charles' law too. And how they combine to give us the ideal gas law. So first of all, the weight of a fluid, atmospheric pressure rises or results from the weight of a fluid at sea level. So we have this 1 square meter thing in the floor right here, and it's like there's 1,000 big old football players standing on top of it because there's 100,000 newtons of force applied over this 1 square meter area. 100,000. That means that if I imagine this square, and then I start sort of building a column around it, and I take that column all the way up to space, and I could take all the gas that's in that column, and I were to weigh it, what would be the weight of that column of gas? It would be equivalent to how many football players? What would be the weight of the gas? If I took all the gas in a column that went all the way up to space, all the way up to the edge of our atmosphere, what would be the weight of the gas that sits on top of this 1 square meter? Now, the pressure on that 1 square meter is 100,000 newtons per square meter. That's 1 atmosphere. So what is the weight of the column of gas that goes all the way up to space? No, it has a weight. Like gas definitely has a weight. It doesn't feel like it has a weight because we can, move it around, but it definitely has a weight. It's made up of, nitrogen and oxygen and things that actually exist. They're matter. What do y'all think? If there's 100,000 newtons per square meter of pressure on this 1 square meter, that means there's a force of what on this 1 square meter? No, not 1. You're still not wrapping your mind around the fact that there is 100,000 newtons of force acting on this floor right now. 100,000 newtons of force. Like that just doesn't seem right to you, does it? But it's true. What if it just fell through? There's 100,000 newtons of force. Where does that force come from? The atmosphere. So if I were to but see the column of fluid that goes up all the way up to the edge of space, how much does it weigh? That amount, 100,000 newtons. That's where that force comes from because it has 100,000 newtons of atmosphere sitting on top of it. In fact, you right now, what's the force acting on you? You probably got your body surface area is probably a couple square meters, right? Or no more. Yeah, no, maybe 2 square meters-ish. That means you have 200,000 newtons of force acting on you. Do you feel the weight of the world just bearing down on you right now? Can you feel it? Okay. Well, that atmospheric pressure results from the weight of the fluid. So if I imagine on my square of floor that's 1 square meter, that means that the column of liquid, the column of fluid that extends all the way up to space, that it has a weight of 100,000 newtons. And all of that weight drives down onto our 1 square meter. Now these floors are pretty good, these terrazzo floors, but they're not really built to withstand 100 football players standing on one block. So what's the deal on the floor? Why doesn't it just crash down to the ground? No. What? Why? Do I have an answer? Yes. Thank you. So there's an atmospheric forcing up, but there's also another pushing up that's underneath the building where the cats live. So there's a force that's pushing up in that direction, the atmospheric pressure, but then there is also another pushing in that direction. And so that's similar for us. So though there's an atmospheric pressure pushing in this direction, but I have a similar pressure pushing in this direction. Okay? Unfortunately, I'm mostly water, and water is incompressible, so it doesn't really change my shape. All right, so we can derive this pressure. It's not that hard. We can consider a column of fluid. Remember, that's liquid or gas as a fluid over a particular point. Like, let's say that I have a big container, and I have a point right here, and I want to know what is the pressure at that point. I imagine that I make it into my 1 square meter, or just some surface that has an area A. And then I imagine my big column that goes all the way up to the top, and I fill it up. I imagine what is the weight of the fluid that fills that column. The weight of the fluid is equal to m times g. Right, that's Newton's second law. This is the mass of the fluid times the acceleration due to gravity. Let me introduce an idea. I'm sure that you've heard it before, but let me just make sure that you are aware that density, that describes the amount of mass per unit area, rho is equal to m over v. That's our definition for density. That's on your equation sheet, I think. No, it's not, actually. But the density is mass over volume, and that means that I can rearrange this, and I get mass is equal to rho times volume. All it is, I just multiplied both sides by v. It got rid of this v and moved it over to that side. You guys familiar with density? You've had density before. You should have had it in middle school even. Density is just a measure of how much mass per unit volume an object has. So marshmallow or aluminum, which has a higher density? Marshmallow or aluminum? Marshmallow has a higher density? Aluminum. There's more matter packed into a unit volume of that. All right? So more dense objects have more matter per unit volume. Now I can take this and plug it in right there. So this is equal to the density of the fluid times the volume of the fluid times G. Now, I can say then that pressure is equal to force over area. So my force is what I just found, that density of the fluid, volume of the fluid, times G divided by A. And A is the area of this block, sort of the bottom of that rectangular prism. And to get our final expression, you don't need to know how to derive this, but I think it helps to sort of illustrate where this pressure comes from. V over A. What is V over A? Volume over area. Well, I know that volume is equal to area times height. So what is volume divided by area? Height, yes. So when I talk about millimeters of mercury, I'm talking about height of that column. So the V over A is equal to H. And so my expression then becomes, for pressure, density of the fluid, the height of the fluid, and then G. Usually write it as rho GH, so I'll write it there. So that's my expression for pressure. That is on your equation sheet. That the pressure due to a height of a column of fluid is equal to rho times G times H. So for example, if we took, I don't have these numbers right off, but if we took the density of the air that we have right now, and we multiplied it times 10, and then we multiplied it times the height of the atmosphere, then that's where we would get that 100,000 newtons per square meter that we have at 1 atmosphere.
Is that a P?
No, that's not a P. That's the Greek letter rho. Right, so this is rho. It's different from my P because I put a base on my P. It's sort of like a lowercase p, except it's got a big curl to it. All right, so pull out your Greek alphabets. Alpha, beta, gamma, delta. Yeah.
What did you say for?
The gravitation or
Okay.
acceleration. That's the 10 meters per second squared. Remember from last chapter, if we wanted to know the weight of an object, we multiply the mass times the acceleration due to gravity. That's our Newton's second law. F is equal to ma. Okay? Y'all excited about this? No? You look a little bit excited. Like, I know that you're saying that on the outside, but I know that inside your heart, yes, woohoo! You're excited about it. As depth increases, as I go deeper and deeper into my fluid, the pressure will increase. Let's watch a little video. What would happen if the fluid, or if the bottle was not filled with air? That's what I had in it now, air. But instead it was filled with water. Yes, water is incompressible. So we'll get to that in a little bit. But some liquids are compressible, and some fluids are, some fluids are compressible, and some fluids are incompressible. Liquids, compressible or incompressible? Incompressible. But other fluids, like gases, those are compressible. We'll see that a little bit later when we get to Pascal's principle. So if it was just filled with water, nothing would have to take it down. It would just sort of stay how it is. Same for us, that we're mostly incompressible because we're mostly water. What's that? Mostly, right. All right, let's look at atmospheric pressure. We said is really, really big, right? 100, I'm not going to stop there, 1,000 newtons per square meter. But it's difficult to imagine because our net force is 0. So if I have 100,000 newtons on this side, then I also have 100,000 newtons on this side. I'm not really going to feel it, just because it's not moving me around. I feel a net force of 0. I have some ways to observe it. We can use a barometer. Not sure if you've ever seen a barometer, but you've certainly heard of the measurements from a barometer. A barometer looks like this. You have a tube, oops, that's open on both ends, and it's filled with some liquid. The first barometer was filled with wine back a few hundred years ago. But they had a problem with it because the column of liquid, if it was filled with wine, was really, really tall. And so it just wasn't very practical. It was like 30 feet tall, it had to be. And that's why they use what for barometers? What do we use in barometers? We also use them to measure our blood pressure. Mercury. And mercury is a much denser liquid than wine or water. But in a barometer, we have a pressure, like our atmospheric pressure, on this side, and then we measure how high it causes that liquid to go up into the column. And then we take the difference, we take this height, h, remember that pressure is equal to rho times g times h. And so the atmospheric pressure, if I wanted to measure it, would be equal to the density of mercury times the acceleration due to gravity times the height of that column. And at sea level, what is the barometric pressure? Anybody know how many millimeters that column of mercury is going to be at sea level at 1 atmospheric pressure? It's a number you've heard before, and I tell you, I'm certain that you'll remember it. That's right, 760 millimeters of mercury. And so at 1 atmosphere, this value for H is equal to 760 millimeters of mercury. That, by the way, is where we get that unit, millimeters dash Hg. That is a measure of our pressure. Okay? Another way is with a newspaper. See, I have a couple of videos I want to show you. I'm just going to stop the recording because YouTube doesn't like me to post recordings of its videos.